With that, I hand over to the interesting presentations, to the user presentations, and I would like to welcome David Abramson from the University of Queensland, and he will talk a bit about what he's doing with us in building infrastructures for data and Ceph sciences. David.
Thank you very much. I can't promise it will be interesting, though. I've been asked to talk a little bit about some of the things we're doing at UQ. UQ is the abbreviation for the University of Queensland. I'm going to talk a little bit more generally than just the data infrastructure, and I'll add something about the compute as well. So let me start by giving you a little bit of context. University of Queensland is a fairly large, complicated university. I think we have around about 50,000 students, mostly concentrated on one campus, but as you'll see in a moment, there's some complexity in the way the infrastructure is distributed. I head a group called the Research Computing Centre, whose brief is to sit between research, and that's any research, and advanced computing infrastructure. So we are separate from the IT services group in the university who deal with more of the routine equipment and services, and our focus is largely on high-performance computing, large data storage, and advanced collaboration tools, or in fact advanced tools in general. And the argument is very simply that you don't want to take a good researcher in their field and turn them into a bad computing person. And the gap, what I often call the impedance mismatch between where research is and where the infrastructure is quite substantial. So on a daily basis we come across researchers who are very, very competent in their field, but just need some help to use some of this infrastructure. And so we've built a centre. This is my so-called onion diagram, which describes how we work. And it's got a multi-tiered structure that allows individuals to interact with experts in different areas at the appropriate level. So if you go to the middle of this, and I just want to spend a minute describing the context for you. If you go to the middle of this, there are systems and there are people who know how to operate those systems. And in some cases, researchers will simply say, give me a Unix prompt or a Windows prompt, I just want to do X, Y, Z. Give me an account on a machine, I know exactly what I'm doing. And so we provide pathways where researchers can go directly to those people. More often than not, though, they need some assistance, and we've chosen 5 core technology areas, and you can argue with me at the pub or at the party tonight about whether it should be 5 areas or 6 areas or 2 areas, but we've chosen 5, and these are vertically stacked software systems for doing certain things, and so these are cloud computing, high-performance computing, workflow systems, data management software, and visualization. And the argument is that in order to do research in really any of these fields, you may use one or more of these systems. And so we often draw a little matrix that shows which technologies are used in certain projects. So you could imagine one project might need high-performance computing and visualization, another one might need cloud computing and data management. And you can just imagine having little X's in the appropriate columns showing which projects make use of which technologies. So we have expertise in those areas, and again the same model applies, that if someone knows they want to do something, they may come to us and talk about the problem, and we may say, well, you need some help with, say, workflows and cloud. And we'll build a little ad hoc team that focuses on that. It works on the problem, then it disbands. Now, for some researchers, that's still too much of an impedance mismatch. And so there's another layer on the outer onion ring there, which is the domain level, in which we have people who can talk both into the diagram and out. And these are typically dual-branded or dual-funded people that sit in the research groups. So you might find, for example, biosciences is one of our larger engagements. And there are people who can talk both in and say, well, we know what to do with, say, cloud computing in a particular biological sciences problem, but they know enough about the domain to also work in that. And so there are different levels at which people interact, and we don't try and get in the way of anyone who knows exactly where they want to go, but we try and assist those who don't. Now, the outer part of this diagram is the complexity of UQ, and that is that there are a very large number of very competent researchers in what are, in some cases, vertically siloed. And so I don't have to explain to you what all of those various acronyms are, but you can guess that they're various faculties and institutes and centres around the university. And they're clustered around these themes. And so we can't dictate to any particular user group what systems they might use, but what we can do is try and encourage some economy of scale. And it looks like I've actually got an enormous group of people. I don't, and this is very much like an electron cloud, that if you look at any point in time, you may not be able to say exactly who is the expert in workflows and who is the expert in cloud. But we deliberately portray this as the model. So that's contextual for you. I don't really want to say anything about what's the big deal about data. You're all here for a particular reason, but we all know this is exponential growth, and this provides challenges for researchers. And I should have said when I started this talk, I'm absolutely not a data expert. I've been sucked into this vortex by what's happening and standing back and saying, can we do a better job of the infrastructure? So there's been a very large investment in compute and data infrastructure in Australia. There are various acronyms that have been funding this to date. RDSI and Nectar are the two prominent ones. And there's a cloud node in Queensland, in the state of Queensland, called Chris Cloud. And that's in a data centre called Polaris. So you'll see a little bit more of this in a moment. When we talk about data-intensive computing, I don't want to separate data management and storage from compute. Too often the debate separates these two things out, and then suddenly you're left with all the compute and no way of storing the data or accessing the data, or vice versa, data that doesn't actually get computed of. And I often say to people, if you've got petabytes of data, you don't want to look at it on a browser. And too often the focus is around archiving and storing it, and not around actually digesting it or generating it. So we find there are plenty of applications generating data. On the left-hand side there, there's sort of your generic picture of instruments generating lots of data that go into maybe data mining and analytics programs because it's simply too large to do anything else with. But on the right-hand side, you can see we've got extremely powerful, complex models that are generating data at enormous rates that also get pushed into some of the similar analysis software. So it's enabling those pipelines that's of interest to us. So here's a little bit about the landscape, and with the Brisbane region underneath there, but this is the UQ main campus. And then around about 30 kilometres away, we have our large data centre, which unfortunately doesn't actually house all of our infrastructure. So this is a commercially run data centre. If you haven't ever seen a real data centre, and I haven't had much to do with this over the years, it's pretty scary. It's got everything by way of all of the cooling, low PUE, and the like. And so we just pay for tenant space in that. And I'll show you what equipment's out there, but there are some clusters. There is some of our storage, in fact, a lot of our storage. But then on campus, because of the decentralised nature of UQ, there is also a significant amount of compute infrastructure that I have no control over at all. And there's a very large amount of scientific instrumentation. And so people often talk about co-locating the data centre with the instrumentation. I can't even get into that data centre, it's so secure. I'm certainly not going to go and put an MRI scanner or a microscope out there. So it's almost an imperative that we'll have distributed infrastructure. So what we've been building over the last year is a fabric, a data fabric that sits between that. It's called Medici. And the idea is to have as much of our storage as possible in the data centre. That's the right place to be putting the storage. We also have very substantial compute systems out there and clouds that can access it, but also, as I've pointed out, a lot happening on campus that needs to access the same data. So this is the game where you can't win. The distributed data is further from both the instruments that generate it and some of the computers that process it and the researchers that interpret it. And so what people finish up doing at the moment is manually moving data around. Now, I don't like manually doing anything I don't have to do, but just think about it for a moment. Yeah, of course you can write scripts that move data around, but where is the data? When did you last move it? Where's the latest copy? There's just so many provenance issues around managing that data that make it complex. So Medici solves this by adding on to the existing infrastructure, implementing on-campus caching, and I'll make something of that in a moment, and doing automatic data movement. This is a little bit of a network map of our data centre, which I will not talk about, other than to highlight that it is moderately complex. It took me 2 years to get someone to draw me a picture of the data centre and what's out there. Now on the top right-hand corner is the bulk data storage. This is an SGI DMF managed silo. For those of you who know the SGI product range, and with NFS shares back out to the rest of the infrastructure. So this is the cloud, and there's various high-performance machines that I'll talk a little bit more about in a moment. But the majority of the data sharing around there is done by NFS over a data center switch. So just park the idea of there being our bulk storage in an HSM managed by SGI. There are also a number of DDN products providing bulk storage. There's multiple petabytes of storage in spinning disk with some different products, and Justin will correct me if I've got the product names wrong because he keeps telling me I make them up. But then you guys keep changing the product names, Alex. So we have a grid scaler device down here serving a couple of our clusters. I'll come back to that. And then some bulk spindles at the top there providing NFS storage out to, as I said, out to the rest of the fabric. So a lot of the spinning disk is actually in DDN equipment. Not all of it, but a lot of it. Now the thing that people seem to have forgotten over the years is that caching works. The reason your laptop works is because there is both spatial and temporal locality in the data. So this whole idea of moving data around manually is making it much harder than it actually has to be. So what we wanted to implement and what we have implemented is a structure that caches data at the campus or at the place where it's been accessed. So bulk storage out at Polaris, that's where there are tens of petabytes worth of disk and tape storage, but accessed on campus and either generated on campus or consumed on campus. So we put a cache close to the devices that generate it, the users that view it, and the systems that interpret it. So think about this as just one possible pipeline, one exemplar of how this can work. Data may be captured on an instrument at St. Lucia. You may do some pre-filtering and analysis of that data. You may remove some of it. Often you get nothing back from the instrument. That data is then moved to Polaris for processing, which could be on the cloud node, the Nectar nodes, could be on, say, Flashlight, which is a high-performance parallel machine, and then possibly moved back onto campus for later visualization. In the process, it may well get archived into this, this hierarchical storage. So when you put caches in places that you want to access the data, you find the data actually migrates to the place that's working on it. So for supporting that pipeline, as I said, you may have multiple instruments on campus on the left-hand side there generating data that's dropped into a cache. At some point, you'd like that data to migrate to where the processing's occurring, which could be out at Polaris, and you certainly want it to migrate out to the storage system. When I say certainly, there are actually cases where you want temporary storage and maybe you don't want it to go anywhere. You just want it to be local. And what we've been observing over the last N years is people putting in SANs. They invest in a SAN in a particular department, they go out and buy it. It could be tens or hundreds of terabytes, and it's isolated, it's siloed. What happens when they run out of storage there? What do they do about backup? So the whole idea of putting caching is that there's one consistent data fabric across all of those systems, but the amount of storage and the performance for that storage will be exactly equivalent to what you would have got if you put a SAN out there. So the storage architecture looks a little bit like this, and that is that we have on the right-hand side long-term data collections stored in HSM. I sound a little bit like a reused SGI, IBM, DDN salesman these days, so please forgive me, but I'd argue that DMS is probably best of breed in HSMs from what I've seen. So long-term storage out there with cache management on spinning disk. That's then sent out to and acts as the home for a parallel file system based on GPFS, or as you've just heard about, spectrum scale. That happens to be done over NFS at the moment. And I want to highlight that this is the bit that both IBM originally and SGI originally said won't work. So we've got long-term bulk storage as the home file system out on DMF, but cached distributed file systems on a GPFS cluster in a DDN device. That's then shared out into the compute as a parallel file system. So I've got the best of parallel file systems on the left-hand side and distributed file systems on the right-hand side, seamlessly moving data between them. If you look at the sort of services we actually want to support then, you've got managed data, which is deeply managed. So there are a number of software stacks that look after capturing the data from instruments, tagging it with metadata, archiving it and exposing it to tools. We've also got unmanaged data, which is data that just people drop in folders and want that to be reliably archived and processed. There's a discussion on campus about what we do with clinical data, and I don't have time to really talk about that. And then there's cloud access, which I would argue is largely for wide area distribution. I've done some work, I've written a paper, here's a URL for the data. You can download that and do what you want with it. All of that is sitting, will be, sitting seamlessly on top of this fabric. I'm probably running out of time, but I haven't touched on identity. Identity is a bit of a nasty thing that hangs around there. We don't have a single UID space across things. We actually do across part of the university, but not all of it, and certainly in terms of the wider Queensland region, we don't have a single identity space. And so there's the need to map between UID spaces, and there's some things in GPFS that allow you to do that. Object storage is becoming increasingly important. We started out with no one saying they wanted object storage, and now we're getting more people saying they want object storage. And as you just heard, SpectrumScale has done quite a nice job of unifying Swift on top of GPFS. And so we plan to use that for distribution of wide area storage. So we have a proof of concept implementation at the moment. There are 2 DDN GS7Ks. These are the SpectrumScale devices on campus. There's another DDN SpectrumScale device at Polaris that serves the parallel file system into our 2 compute clusters, one called Flashlight and one called Tinaroo. These are 2 high-performance machines. And there's currently an IBM ESS out there on trial at the moment. And then there's a list of users around the university where we're doing initial trials. Queensland Brain Institute is one of the largest, and they do a lot of genomics and image processing. There's nanotechnology, there's Centre for Advanced Imaging, various science users, microscopy, all of the sorts of users you'd expect to have from a large university. I'm going to skip over that last bit and just reiterate the fact that caching works. It also fails, and we know the pathological cases in which caching fails. If you ping between readers and writers, we know that you'll get data moving all the time. So you try and avoid that. As it turns out, most of our research workflows don't do that. As I said, so there are multiple DDN devices in there running GPFS across the wide area. We're currently looking at refactoring some of our SFA 12Ks that are just disks and turning them into some SpectrumScale devices. We've yet to implement the UID mapping, and we're certainly interested in rolling this out to other components in the Queensland region at least. So I think I'm pretty much on time. Thank you.